Okay, so we're going to look at the next example, and let's have a look at part A. It says that p of x is a polynomial with integer coefficients. Show that if alpha is an integral 0 of p of x, then alpha is a divisor of the constant term. Okay, so let's start off with how we're going to approach this question. We're going to start off by defining what p of x is. Okay, so let's change colours here. So for our solution, part A. All right, so what we're going to do is we're going to start off by saying what is p of x equal to? P of x is just some polynomial, so p of x is equal to an x to the n, an minus 1, x to the n minus 1, plus, keeps going, you'll have a1x plus a naught. Okay, and we're told that the coefficients are integers. Okay, so we're going to say where a naught, a1, a2, all the way up to an are integral. Now that's another way of saying integers. Okay, you'll see that sometimes in textbooks. So we just said that the coefficients an minus 1, a1, a naught, these are all integers. Okay. Now, part A says show that if alpha is an integral 0, so that means that a 0, which is an integer, then you've got to show that it's a divisor of the constant term. Okay, so let's plug that in. So let's first of all find what p of alpha is. So, well, we know that p of alpha is an integer 0. So we know p of alpha is 0. Okay, so that's something we know. So straight away we can write down that 0 is equal to, now just subbing in alpha where the x is, so you're going to have an alpha to the n plus an minus 1 alpha to the n minus 1 plus a1 x plus a, actually no, we don't have an x there, we should have an alpha there. Get rid of that. That should be an alpha. Okay. Now, it says we've got to show that alpha is a divisor of the constant term. So the constant term is just here, isn't it? There's my constant term. So I want to show that alpha is a divisor of the constant term. So what we could do is make the constant term the subject. Okay, so if we do that, a naught, that means everything on this side will be negative, won't it? So you're going to have minus a n after the n plus a plus plus a1 alpha. Okay, so we've taken a naught on one side and put all the terms on the other. Now, next thing we're going to do is take out a common factor because we want to show that we can divide by alpha. So next thing I'm going to do is just take out the alpha here. So I'll take out alpha as a common factor. So I still have an there. And this will be alpha to the n minus 1. Okay, so because alpha times alpha to the n minus 1 is alpha to the n. Plus an minus 1. This will be alpha to the n minus 2, because when I multiply that by alpha, I'm going to get n minus 1 to the power, plus a1 alpha. Actually, no, that won't be a1. It'll just be a1, won't it? Don't need that there. Okay, so just a1. So we've taken out alpha as a common factor. And then all we've got to do is divide by alpha, because that's what it says. I've got to show that alpha is a divisor of the constant term. So I'm just going to divide both sides by alpha. So a naught divided by alpha is equal to minus brackets a n alpha to the n minus 1 plus a n minus 1 alpha to the n minus 2 plus a1. Okay, now we're almost there. We have to prove that it's divisible. That means when we divide a naught by alpha, we get some sort of integer. Well, we know that all of this must be an integer because we know all the constants, all the coefficients are integers, don't we? So we know an minus 1, a1, they're all integers. We know that alpha is an integer as well. So what we can say as a result of that is we can say therefore a naught divided by alpha is equal to some integer, right? We know that the whole of that brackets is an integer, don't we? So, and a minus sign times an integer is still an integer, isn't it? So I can just say is equal to k, where k is an element of the integers, okay? Right, and we're going to say obviously what is k equal to? K is equal to the right hand side. Okay, so I'm just going to say where k is equal to the right hand side. And the right hand side includes everything on the right hand side. So that means the minus sign as well. So all of this here, we're going to call that right hand side. Right, that'll save us having to write it down again. K is equal to the right hand side, and as I said before, we know that alpha is an integer, so that means the entire expression in brackets is an integer. Okay, so therefore alpha is a divisor of the constant term. Okay, all right. Now part B says show that if beta equals P on Q is a rational zero of P of X, where P and Q have no common factor, then P is a divisor of the constant term and Q is a divisor of the leading coefficient. Okay, so we're going to actually set this up in a very similar way to the first proof. Okay, so what we'll do is we'll just do a snapshot. There we go. I'll just take a little snapshot of this part of the question. There we go, and I'll just bring that down to the next page. Okay, so let's just paste that. Just here will do. All right. So let's start off by substituting P over Q into my polynomial P of X. So P, now I've already defined P of X on the previous page, so we're just substituting P on Q there. So if I do that, I'm going to get A, N, and P on Q to the N will be P to the N on Q to the N, right? Then plus A, N minus 1 p n minus 1 over q n minus 1. Okay. Okay, it's looking good. And then we're going to have a whole lot of dots as before, plus, and then we're going to have A1, P over Q, and then we've got A0. Okay. Now, what do we know? We know that this is a rational zero. P over Q is a rational zero, so we can say that P of P over Q is equal to 0. Okay. So that means 0 is equal to this whole thing, isn't it? So rather than writing it out again, what if I just put equals to 0 here on the end? Okay, because we know that's true. Which means I can rub this out. And maybe I should have put that up ahead. I could maybe put it up here. P of P over Q is equal to 0. Okay. Now, we've done that part. We've subbed in the 0. And we've got to prove that P is a divisor of the constant term. Okay. So, and Q is a divisor of the leading coefficient. Okay. So what we're going to do then is, first things first, we're going to clear these fractions out of the way. Okay, so if I multiply everything by Q on N, so let's do that. All right, so we're going to multiply by Q to the N. All right, that should get rid of all the fractions. So that means you're going to have, we'll have 0 here is equal to, now this will just be AN P to the N plus AN minus 1 P and minus 1, and that'll be Q plus A1. The P term will stay as it is, and this will be Q to the N minus 1, and then we've got plus A0 Qn. Okay, so we've cleared the fraction, and what we're going to do next is we want to look at the term with a constant term, don't we? So A0 was the constant term, wasn't it? There we go. A0 was a constant term. So if we put that on the other side, okay, and we've got to prove that P is a divisor of the constant term. So we're going to put this term on the other side, okay, and notice that all the other terms have a P in it, all right, because we want to prove that P is a divisor of the constant term. So I'm going to put the constant term on the other side. So you're going to have minus, well, the term containing the constant term, which is, we know that A0 is the constant term. So this is the term containing the constant term. Okay, and then we're going to simultaneously take out P as a factor. Okay, so that'll be AN P to the N minus 1 plus AN minus 1 A minus 1, so it'll be P and my, now where's my Q term? Okay, no Q term there, there'll be a Q term here. This will be Pn minus 2, and then we've got the Q, and then we're going to have a plus, and dot, 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 then plus, we're going to have an A1 there. Now P is a common factor, okay, so all we've got left then is the Q and minus 1 bit, then a close the bracket there, okay. So we just took out P as a factor for these guys here, and don't forget we put this term on the left hand side. All right, so we can then divide both sides by p, can't we? So we're going to have, and if you like, yeah, so let's have a look at this. Minus a naught q to the n divided by p is equal to an p to the n minus 1 plus a to the n minus 1 p to the n minus 2 q plus plus a1 q to the n minus 1. Okay, now that minus sign, we could leave it there, but if we just want to be pedantic, I could put that on the other side, couldn't I? There we go, minus. All right, now we know that the right-hand side is an integer, isn't it? Because we know all the coefficients. Okay, all the coefficients are integers. We know that p and q are also integers. Okay, so that right-hand side is the whole thing is an integer. Now, that means a naught q to the n divided by p is some integer. Okay, so we're going to write that down. So therefore, a naught q to the n divided by p is equal to some integer, right, where k is an element of the integers, right? So we know that. Now, the question tells you that p and q have no common factors, okay? That means p cannot divide into q at all, right? That means p must divide into 8 naught. So I'd say, but p and q have no common factors. Okay, so therefore p divides a naught. Therefore p divides the constant term a naught. Okay, now that's one part of the proof, because the other part was to prove that q is a divisor of the leading coefficient. Okay, so q is a divisor of the leading coefficient. Okay, so come back to the original expression, which is here. All right, now we need to look at a term involving the leading coefficient, which is an p to the n. So what I'm going to do this time, I'll do this in a different color, is I'm going to put the an p to the term on the left-hand side, then I'll keep the rest of this, including the term containing the constant term, on the right-hand side, okay? So I'm going to put this on the left, or vice versa. You could put everything, the other terms on the one side. It doesn't matter. So let's do that. So let's just change colors. Okay, I'll do some black. So I'm going to write down also, we could write this down, minus an p to the n, okay, is equal to, right, and it's going to be equal to the all these terms here. So an minus 1, pn minus 1q, that's the next term. So an minus 1, p to the n minus 1 q plus a n minus 2 p to the n minus 2, and that should be Yeah, that'll be q squared then, won't it? The next term. Oh, that's an extra term I've included that wasn't up there before. Plus dot 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 plus, and that'll be a naught q to the n. Okay, so that's that last term there that we used before, so that's on the end. Now we've got to prove that q is a divisor of the leading coefficient. So I'm going to take out q as a common factor next. Okay, so I'm going to have minus a n p to the n. I'm going to now take out q as a common factor. It's going to be a n minus 1 p to the n minus 1 plus a n minus 2 p n minus 2 q plus dot 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 plus a naught, and that'll be q n minus 1. Okay, now we're going to divide both sides by q. So you're going to have minus a n p to the n divided by q. So you can see the proof is following the same steps as before. And you're going to have a n minus 1 p to the n minus 1 plus a n minus 2 p to the n minus 2, and there'll be q there, plus dot 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 plus a naught q to the n minus 1 close bracket. Now I can get rid of this minus sign if you like. I can put it on the other side. There we go. Now we know that the right hand side, this is all integers, isn't it? The coefficients are all integers. P is an integer, q is an integer. So the right hand side is just an integer. So we'll say therefore a n p to the n divided by q is equal to some integer. Doesn't matter what you call it. Let's call it m. Right, where m is an element of the integers. Right. Now we know that q and p have no common factors, so q must divide the leading coefficients. So, but P and Q have no common factors because they told us that in the question. Right, so therefore Q is a divisor of the leading coefficient. Of the leading coefficient AN. AN is the leading coefficient. Okay. All right, so that's A and B done. What I'll do now is I'll just do a separate video for C.